Okay, sweet. Sorry about that. So what I want you guys to do is kind of navigate back to the first folder that we created. So the one with the setup where we set up the environment and stuff. And then from there, I want you to extract so go into the data preparation. So once you extract the zip file that you downloaded, go into the data preparation folder. And then here you'll see a set of files. So we'll be working on the Titanic dataset. So I've kind of already set up a Python notebook for this. So you should see like titanic.ipynb. So that's a notebook that we'll be starting on today. If you want to work alongside with me, I'll kind of do some live coding as much as I can. And I'll show you kind of my thought process of what I'm doing when I'm cleaning the data. And then the file here, the final one, that's kind of has the complete answer of what I've already done. So if you want to jump ahead, you could also look at that. But it's basically just, follow along, try to listen to what I'm trying to say, and I'll explain what I'm trying to do. So you would want to copy these files, so the Titanic notebook files and the data folder into the folder that you created before. So it'll be something like this. So you do that in the file explorer of Windows or whatever for Mac. And then from there, you can open up Jupyter Notebooks. So I'll give you guys a minute to do that. And if you need any help, just raise your hand. If you guys are able to get to that point, we'll just start with the Titanic notebook. So you can just open that. Sweet. So I think most people seem to have the notebook running. So I guess we get started on the kind of data cleaning, pre-processing part. So basically what we'll be going through is kind of what you would normally do when you receive a kind of a brand new data set. So, when you work and kind of your manager or boss gives you a project and you get given a huge data set, what you want to do first is to kind of have a look at it, have a feel of the data, see what kind of all the variables are, what do they mean, are there any like kind of weird distributions you need to take care of, how much data is missing, how you want to deal with that before you move on to more of the machine learning stuff. Because the machine learning algorithms are only good if your data is good, because you pass in your data, the machine learning algorithm will try to learn based on what your data is and then produce a predictive model, and from there the accuracy of that model will have to then depend on your training data. So that's why we have to, as a data scientist, you probably have heard that like majority of the time is working on cleaning the data, kind of the pre-processing, versus actually the modeling part. And that's really true, because you need to really understand what's going on in your data before you move on. So that's why we're kind of doing my section first before we go back to our Peter section on the machine learning stuff. So the Titanic dataset. So I think if anyone that's been in Kaggle or want to start learning data science, they probably already come across the Titanic dataset. It's one of the most, I guess, used dataset to kind of start learning data science. So you can get it from this link here that I put in the notebook. I'll just take you to the Kaggle. That's where I got the data from as well. And when you download the data, it's already been split up into like a training set and a test set. So the training set is basically what you would use to train the machine learning algorithm. And then once you train the algorithm and get a model, you would then use the test set to produce kind of like predictions. So when we first approach this cleaning stuff, we kind of have to have a kind of systematic way of doing it. So whatever you do on the training set, you got to do the same thing to the test set. So you got to make sure it's consistent. So before we get started to cleaning the training set, so we'll have to look at some of the variables that's already that exists in the data. So if you have a look at the data, if you open the file explorer and then go to the data folder and go to the raw data. So and if you open up test and I'll train, sorry, this is the raw data you get from just straight downloading it off Kaggle. So I've kind of summarized a bit of information about what these variables are. So, okay, so the main variable we are interested in is the survival rate. So like, given So given the person, did they survive or not? So 1 for yes and 0 for no. So they also have all these other variables here that kind of we are trying to use to explain this survival rate, basically. So what we can see here, the survival variable is the response variable. So this is kind of what we are interested in and what our model wants to predict. And all these other variables are the explanatory variables. So they kind of explain the variation in the survival data, the survival variable. So, I guess most of this is self-explanatory. So like P class is like the class of the person. So they low class, high class, middle class. Sex, just male, female. Age, how old they are. These two might be a bit confusing, but it's defined in Kaggle as the number of sibling and spouses related to that person. And Parch is the number of parents and children related to that person. So it's kind of describing like the family size of that person. You have the ticket number, the fare, so how much the ticket cost, the cabin, so where did they stay on the Titanic ship, and embarked, where did they embark from the location. So yeah, so these are the main variables we'll be looking at. So we can get started now, once we understand what the variables are, with the first bit of cleaning the data is to do some exploration. So we need to kind of explore in more detail how these variables are kind of look like what's the distribution of them, how do they relate to each other, and is there any outliers and stuff like that. So the first chunk of code here is just setting up everything. So I'm assuming you guys have a little bit of knowledge in Python and stuff, since everyone seemed to put their hand up when we said you guys have installed Python. So you just first start off loading the libraries that you need. So these are the ones that we'll be using for the cleaning. Next, we'll just load in the data. So this is loading the data. So before, as you can see, we save the data into like a folder like this, and we have a folder structure where the raw data is in its own folder. So that's kind of what I'm doing here. I'm just reading the training data, the test data in. So I'll run this chunk of code, which you guys should do as well. So if you're not sure how to run it, you can go Control-Enter in the cell and it'll run it, or you can click the run button up here. So whatever cell you're selecting, like if it's selected, it'll be like green like this. And then you can click run and it should run that cell.
It's Shift-Enter on Mac, I think.
Oh, okay. Yep. See. Yeah. So once you read the data in, we can kind of have a quick look at the data. So this is what this line is doing. So we stored the training data inside this variable. So now we want to kind of have a look at what the training data looks like. So, run the cell again, and it should print out this. So this should look pretty familiar if you've already opened the CSV. It's pretty much just putting the first couple of lines of the CSV file. And you can see kind of all the variables that they're there and kind of the first 5 observations. So pretty standard stuff, what you would normally do as well. When you start looking at a brand new data set, you just have a look at what it looks like. Then you move on kind of to have a look at the summary statistics. So what this is kind of just summarizing each variable, and you want to look at kind of like the distribution of the variable, and if there's any skew, if it's right skew, less skew, normally distributed, or if it's a categorical variable, not numerical form, just with different levels or categories. You want to look at which categories are more frequent than others and stuff like that. So that gives you an insight to what these variables are doing. So what I'm doing here, so the first 2 lines are kind of doing the summary statistics of the numerical variables and the categorical variables. And then the last 2 lines over here, we're trying to calculate the missing values, because when we do a lot of these data science, machine learning stuff, we want as much data as possible. So with missing data, you could throw them away and delete them, but sometimes there'll be a lot of missing data and you can't just do that. So later I'll cover maybe a method of how to deal with these missing data. So right now at the beginning, what you want to do is look at which variables have a lot of missing data. So when you run this chunk of code, so the first output will just be showing you kind of the summary statistics of the data. So, I mean, passenger ID is not much we can really do. It's just the ID of the passenger. So I guess this variable is not that important. Survived variable, this is one of the key variables. We're looking at predicting like the survival rate of someone. So we can see that, the average survival rate is about 38. So 38% of people survived. Yeah, so there's all these other, the variables that were mentioned before, so you can have a look as well. So the most interesting one that we see straight away from looking at the summary statistics is that the fare price, so how much people are paying for a ticket. We might want to deal with. So summary statistics of the categorical variables. So, so name variable is just the name of the individual. So that's not too interesting right now. Sex variable shows that, okay, there's two unique variables, so male, female, and then the frequency, not how many there are. Yeah. So yeah, so for these summary statistics, you don't really want to look into it. It's just mainly just to give you a generic overview of what you want to be focusing on. So I also did some summary statistics of missing values. So this is a bit more important because, like I said before, you don't want a lot of missing values because you don't want to throw them away. They can be useful. So for the age variable, you can see about 177 of those data points have missing age, and a majority of them actually has a missing cabin. So this is something that we might need to deal with other than just throwing it away, which I'll cover in a bit. Sweet. So that's kind of the first main bit. So you kind of do some summary statistics of the data. So once you have done that, what you would want to do next is kind of do some visualization. So do some plotting. So this is, so I'll create a new cell. So with this plus button. And so what I want to be looking at now is kind of the variables. So right, okay, sweet. So let's have a look at the numerical variables first. So I'm just going to copy paste this. So this line kind of selects all the variables that are kind of numerical. So you want to have a look at that first. So I'll do that. So I'll assume you guys know what for loops are. So we're going to do a for loop and loop through each variable and kind of create a histogram of it just to see how it looks like. So I'll just quickly do that. Oh yeah, let me know if I need to slow down anything, if you guys get stuck and stuff. So this is just a simple for loop. So we're looping through each variable, and for each variable, we're going to make a histogram plot. So once you type that, you can. Right. Which one? Oh, yeah. Sweet. Yep. So for passenger ID, that's something that's, I guess, not really that important, just the ID of the passenger. So, and then we can go down, have a look at what other plots we have. So we have the survival variable. I mean, you can just for this one, you can kind of see straight away from the summary statistics that, I mean, around 33% whatever survived. The class, you can see that there's most of the people in low class, some in middle class, and quite a lot in high class. So this is the age distribution plot. So it kind of shows us what's the kind of average age of the people in the Titanic data set. You see there's a kind of strange peak at 0. So quite a lot of, I guess, children or just young babies on board as well. The oldest person is around 80 years old. So this looks quite normal. I mean, you would expect distribution of the age, to be normally distributed, and this is close enough. So probably don't have to do much here. For the sibling spouse variable, we see that most people have a value of 0. So and the distribution is quite skewed. So we could do something here. Yep, and that's same with the patch variable, which just kind of records the number of family members as well. And this is the fair distribution. So we kind of saw earlier the summary statistics is quite skewed. And this is something that looks a bit extreme. So we might want to do some sort of cleaning for this variable as well. So then I'll also have a look at the categorical variables. I might just run through the full completed one just for time's sake. It's already 12:10, so yeah, it might take a while if I code as well. Yeah, so this is kind of what we were showing before, just looking at the distribution of the numerical data. So we saw that the fair variable was quite skewed. So in statistics, sometimes what you would do is if you have a skewed distribution, you'll log it and try to see if you can remove any of the skewness and make it a bit more normally distributed. So this is what I've done here. And so we look at the plot of the log version. Doesn't seem that much better. So maybe there's something more we could do for this variable later as well. Yeah, and then these other plots down here are showing kind of the distribution of the categorical data. So like male, female, where they embark from, because that variable just has 3 different places they could have came from. So we can see that, a lot of these variables, the distribution isn't quite normal, so which is fine. So once we kind of have a feel of what these variables look like in the distribution, we want to kind of see the relationship between them. So what we do here is use a heat map. So a heat map kind of finds the correlation between each pair of variables. So this is a quick and easy way of seeing what variables are correlated. So since we're interested in the survival rate, and that's what we want to be modeling, we kind of just look at the survival against all the other variables. So this is the survival variable, and these are all the other explanatory variables. And the correlation between them, you can see is labeled here. So a quick explanation of a correlation is if it's 0, it means that it's basically not correlated, and if it's 1, it's positively correlated, like exactly. And if it's -1, it's opposite. So if one increases, the other decreases. So any other value in between is kind of just like tells you the strength of the correlation. So the fair variable and survive seems to have a somewhat decent correlation of 0.26. So this is something we know, okay, this variable is quite useful for us that we need to keep for modeling. So we can see the Parch and SIBS SP variable, they're quite low in correlation to the survival rate. Now, this is interesting because you would expect that people who travel in a family might have a high chance of survival because, they'll probably help each other out and, work together to, survive. So what we can see here is that there isn't a strong correlation, but that doesn't mean that there's actually no correlation. So what we need to do is kind of do some work on these two variables. What can we do to make these variables more useful? So that I will cover a bit later as well. So we can see the same thing with age as well. Like you would expect that maybe adults to have a higher survival rate than like a child or an elderly person. So that's also interesting that it's quite low correlation of survival. So that's also something we could look at improving and fixing this variable and try to maybe do stuff that would make it more useful. P class, so that was the class of the individual, whether they were high class, middle class, or low class. And we see that there's a correlation between that and survival rate as well. So this is also quite useful. We will definitely need to use this variable for modeling. So all these other numbers that you see here are kind of useful as well. They kind of show the correlation between other variables, so like age and P class. So maybe the older you are, the higher class you are, which kind of makes sense as well. Yeah, and so then from there, I would move on to kind of doing some kind of plotting between survival and kind of the variables that we just looked at from this correlation plot. So for the sex, females had a higher chance of survival than males. So you can definitely see age is a contributing factor to who survived or not. Same as where they embarked from, so the port that they embarked from. Yep, so this is quite basic, all of this stuff, just plotting and stuff. So, I mean, if you guys haven't done like kind of all these plotting and tools, it might be a bit overwhelming, I think. But what I'm trying to show here is kind of what you want to do with the data when you have no idea what's going on. You want to kind of have a look at the relationship between variables, how they look like, how the distribution is. And you can do that in a lot of ways. I mean, I've done it and I try to make this kind of straightforward, just using some simple plots. So if you haven't covered like Python plotting, you can read on the documentation. It's quite detailed, and they usually will tell you kind of what each function does and how to plot each variable. Yep. So I went with a correlation plot because it's just simpler. You just have all the variables and you just do one plot. You could also do many separate plots, having an x-y axis where x is maybe the fair variable and y could be the survival rate. That could also work as well. But it's just simpler for me to just show you one graph here. So there's like no set way of doing this. So at the beginning, when you explore it, you want to make sure you fully understand the data and figure out what's missing and what you could do to improve it. So I guess after we explore the data, we can move on to the data cleaning part and the feature engineering part. So these two parts, I'll say, the most important, that gets your data set ready for modeling. So there are many ways we can deal with missing data. Like I mentioned before, we could simply just filter it out. And that can be bad because if we have a small data set, it can be degrees of freedom expensive. So what that means is when you're fitting a model and making prediction on like a linear regression, if you're trying to figure out the coefficients of like beta and stuff and the intercept, we have to use data to figure out these values. And the more data we have, the better. So before, you can see we kind of had a lot of missing data if we look at the summary statistics. So for the age variable, there's quite a lot of missing data. Same as the cabin variable. So what you don't want to do is just simply delete those observations from the data set. So what we want to do here is do something called imputation. So what that means is just a way of replacing the missing data with some sort of known distribution. So that could be simply just taking an average of all the known values. So for, let's say, the age variable, we average the age for all the known ages. And then for the missing ages, we just replace it with the average. So that's a kind of simple way we could deal with missing data. So it works in cases where there isn't a lot of missing data, because once there's a lot of missing data and you're just replacing it with the average, it will kind of skew kind of the distribution, make the mean kind of more than the other variables. So that might not be good. So since we have a lot of missing data, we don't want to be using this method, but you could. It's simple. You could also do regression to impute the value. So maybe if age depends on some other variable, you can do some sort of linear regression to then impute and fill in that missing value. So what I'm doing here in this example, I would be mainly focusing on hot deck imputation. So what that is basically, so given you have a variable and it has missing data and not missing data, you take the set of not missing data, and from there, you randomly sample one of those values to then replace the missing data. So what that does is you kind of have an empirical distribution. So you have some values that are not missing, and from there, you randomly take one and put it into the missing value. So that this will kind of keep the distribution the same. So it kind of better than doing an average imputation. So I wrote some notes as well in the notebooks. So if you guys have time, you can read this later as well. So what I'm going to do here is, in this cell, is to clean the age variable. So we saw that there was a lot of missing data for the age variable. So what I did here, so I just created a new column called age imputed. And that's just the same as the age variable. So it will contain all the missing values and the known values. Now, what I'm doing here is, so I figured that before above in the heat map that the class and age variable is quite correlated. So depending on the class of the person, the age will kind of vary. So what I did here to impute the missing values is to loop through each class. So for each class inside this variable, so there was, I think, 3 classes, 1, 2, and 3. So for each of those classes, we figure out the missing, so this is what we're doing. So this part subsets the data for that certain class, and we just store it as a temporary variable here. Then what I want to do is, for the age variable, all the values that are missing, I want to drop them. So this will create this variable that contains only the contain no missing values, and for that class. Then you want to figure out how many missing values there are. And then once you do that, you can use random.choices. So this will randomly create a list of values that will tell you how many samples you want to make from that from the sample of not missing value variable. So yeah, so this is what this part does. So it just indexes all the so for the non-missing value list, you want to index randomly k times. So k is the number of missing values. So once you do that, you will get k imputed values, which then you can use to fill in those missing values from the non-missing value. So that's kind of what I'm doing in this last line. So for the NA values, so the missing age values, you want to fill them out using the imputed data. So this imputed ages comes from here when you, so this drops all the NA values. So this will contain only like values that exist. And then we pass it into random.choices. K equals number of missing values. So that's the number of missing values we have. So this line here will sample the non-missing values and to create a list of values that we can then use to replace the missing values. So that's kind of what this whole loop is doing. This kind of is confusing, I think, at first, because there's a lot of lines here. But what we're trying to do is basically for each variable, for each observation that's a missing age, we're just trying to replace it with some other value that is based on the known values. So initially age, it looks like this. It has these values and it has this value that's missing. So what we want to do is we want to extract all the non-missing values and store it somewhere. And then from that variable, that array of items, we randomly sample the number of missing items we have. So then we can replace that missing value with the randomly sampled value. Yeah. Any questions? Sweet. Move on. So I've moved on to cleaning the cabin variable. So for the cabin variable, if you run the cell, the first part just displays kind of all the unique values of the cabin variable. And we can see that there's a lot of many unique values. So you have a cabin floor and you have the number as well. So what we can do here is that we can remove the number and just keep the floor value to create a new variable called floor. And that'll be more useful than just having the cabin number and cabin floor and number together. So when we saw earlier up here in the summary statistics, the cabin variable has a lot of missing data. And a lot of that missing data is because simply that hasn't been recorded. So that's what you will normally get in practice. So sometimes a lot of data is just missing and not recorded properly. And what you have to do is kind of be smart about it. So instead of just using the cabin variable, we'll create a new variable. So this is kind of feature engineering. Well, what we want to do is from a less kind of useful variable and make it more useful by kind of using some sort of knowledge about what you might expect a variable to be and convert it to something else more useful. So all the missing values, I made the assumption that the people were on like a ground floor or similar floor. So that would be like a default floor. And for all the other values, I simply just took the first letter and that will be their floor number or letter. So that will kind of make this variable floor much more useful than the cabin variable because the cabin variable isn't telling us much. Yeah, so that's kind of what the code is doing here. It's just creating a new variable floor, and from the cabin variable, I'm taking the first element, so the first character, and then for the rest of the missing values, I just fill it with a constant ground floor, and this line should create the variable like this. Yeah. Sweet. So I've done a bit more exploration as well of kind of the class and where they came from, just kind of see if where they came from mattered and the class. You can see that low class people, there's some people that embark from Q and no one in the high classes embark from this port as well. So that's some interesting information. So, and the embarked variable was also missing some values. So we go back up to the summary statistics. Yep, so embarked, there's like 2 missing values. We could throw these away since it's only just 2 observations, but since I've already started showing you guys how to do imputation, might as well just do it as well. So going back down here, so that's what I'm doing, just cleaning all the missing values for the embarked variable the same way that we did it for age, exactly the same. So for each class that there's a missing value, we will replace it with some known value. So that's exactly what we're doing in the embarked variable as well. Then we move on to kind of more feature engineering. So you kind of saw how I made the cabin variable a bit more useful by taking the first letter and using it as a floor, and then filling the remaining missing ones as like a default floor. So we can do something similar with the other variables. So I think we saw that for the age variable, there wasn't a strong correlation that we would expect. So what we can do here is kind of create a new variable called age group that might be more useful. So what I use is this pandas function to kind of split the continuous variable into a series of labels. So basically what this is doing is for anyone's age between this group, they'll be labeled as child, between this group, they'll be labeled as teen, and between this group, they'll be labeled as adult, and this group, they're labeled as elderly. So then we create a new variable, just called age group, and instead of using the actual age values that wasn't as strongly correlated as we saw, we might be able to get some more useful kind of information from just like the groups, the age groups instead. Yeah. So moving on from cleaning the from the creating the age group feature, we can also look at clean the name feature. So before we saw that there's a variable for the name of the individual as well. So the name variable is quite interesting. We can see that it has their last name, their title, first name, and the rest of the name. I mean, when you first look at this variable, you might see there's not anything useful. Like how could someone's name determine if they could have a high survival rate or not? But you can see that they have a title like Mr., Mrs., and etc. So this might also might give us a bit more useful information. So if there a title, maybe say doctor or some important title like captain, maybe that might influence their survival as well. So since there are quite few titles, yep, so this shows kind of all the unique titles that they are. And since they're quite low, I kind of just grouped the remaining ones into a single group with other titles. So this variable will definitely be more useful than the name variable, since the name variable just includes a person's name, and each name will be different and that won't tell us much. But with extracting out the title from the name, might be able to use that in the models to make it, to give us a bit more information. So moving on to to another variable that I created called family size. So we kind of saw that the other two variables, these ones, they describe how many siblings, spouses, or husbands person has. So it's by itself, the variable might not be that useful. So we can just simply add them together, and then also do something similar what we did with age and create separate groups. So if they're between these two values, they're alone because it's 1 or 0. Between 1 and 3, we will make them a small family size, and 3 and 6 medium size, and 6 and 10 large. So we create a new variable called family size. So instead of using these two variables separately, we have a new variable that tells us whether they are alone, they have a small family with them, or etc. So that might be more useful than just simply having these individual variables that might not be as useful, since we saw that most of those values were like at 0 or 1. So lastly, we saw that the fair distribution was quite skewed, and we tried first logging the data to try to remove kind of the skewness, and that didn't seem to help too much. So another method, again, was we could just cut it up into different categories. So I'm pretty sure you guys will be familiar with this, with the above examples. So we're doing the same thing, creating different labels based on which range they belong. So once you complete the training data set, cleaning it, and creating these different variables, these new variables, you have to do the same thing to the test data set. So this chunk of code basically is just copy pasting the above code, but running it for the test data set. And then that's basically most of the kind of cleaning and feature engineering stuff that you would think about doing. So you want to, the main goal of kind of the first part of most data science like projects is to just have a look at the data, clean as much as you can, fill up all the missing values, and create some new variables that will be more useful than some other variables. And to how you would figure out if a variable is useful is kind of look at the correlation between variables and seeing how they would explain stuff. There's a final kind of thing that I want to mention is called encoding methods. So most of these machine learning algorithms, they have a underlying mathematical and statistical formula and stuff. So under the hood, it'd be hard to just pass in like a string and give it and tell it to do stuff, and it might not be able to understand what a string is, and because the underlying stuff of these algorithms is math. So what we do is we kind of have to convert all the categorical variables, so the variables with different groups and stuff, into like a numerical variable. So a way to do that, there's two ways to do that. One way is one-hot encoding, and another way is label encoding. So what one-hot encoding is simply just converting a categorical variable. So let's say we have a variable called animal, and it contains 3 different categories: cat, dog, and fish. So instead of having this single variable, we create 3 new variables, and each variable will be what we call a dummy variable. So it'll just be either 0 or 1. So we'll create 3 new variables. So maybe animal, cat, and then another variable, animal, dog, and animal, fish. So then for each observation, if they are a cat, it'll just be a 1. And so that means for dog and fish to be 0 and 0. So we kind of convert one single column of values into multiple dummy variables based on how many categories there are. So this way, the machine learning algorithms are able to understand, they won't understand that the variable is dog, but they will know that this column will be either 0 or 1, instead of having the previously where we had the variable animal, which will be cat, and they won't be able to understand the string. So label encoding is similar. Instead of creating separate variables, it just replaces the strings into number format. So if it was, let's say, using the cat, dog, fish example, we can just say cat is 0, dog is 1, fish is 2, and then whatever other animal will be 3, 4, 5, 6. And so in that variable, in that column, instead of seeing strings, you'll just have it as a number. Yeah, and that's kind of what this is doing here. This set of code. It's basically doing one of these 2 encoding methods. So this part, the label encoding. So for age group, we saw that there was child, teen, adult, and elderly. So for child, we just say that there was 0, and then teen will be 1, adult will be 2, and elderly will be 3. So that's kind of what we're doing. So for each kind of these variables, we want to do something similar to that. So do label encoding. And for one-hot encoding, these variables, we will kind of create dummy variables. So I can kind of show you if I print this out. Oh. Yep, so I made a mistake here. I put this for loop, this inside a for loop, so it's printing it multiple times. So, but we can still see what I'm trying to do here. So for this variable, we see it was initially like alone, small, or whatever of these categories, and then we just replace them with zeros or ones, and two, 3, 4, whatever, how many categories there are. And I should show you how one-hot encoding looks like. Actually, it might just be easier to see. Yeah, so this is how the CSV looks like after you've cleaned the data. So yeah, so what I mean by one-hot encoding is, so before we had one single variable, sex, and then we'll just have, it'll be either male, female, but we separate into two separate variables. So one variable is sex, male, and then if they are male, it'll just be a 1. So that means they can't be female, so that'll be 0. And then same for if they are female, there'll be 1, and they can't be a male, so that'll be 0. So you have to kind of convert all the categorical variables into this way, because all these machine learning algorithms, well, most of the ones on Python will only work in this way. If you guys are familiar with R, in R, some of the algorithms don't require you to do it this way. So you could have just simply left it as how it was before you go to the encoding stuff. So it'll just be, kind of similar like this, like sex, male, female, and it'll still work. But for in Python, I think in sklearn, which will be what Michael will be using to build the models, if you try to pass this in as is with the variable like this, it won't work. So you would have to do the encoding stuff and then do it and get it to this format. Yeah. So that's kind of my section. I know I kind of went over quite fast. Not sure if kind of got what I was trying to go through, but I want you guys to understand the main themes is to kind of explore the data, clean the data using imputation, and then kind of feature engineering just to make useful variables from not useful variables. This takes practice, and yeah. Sweet.
And then
Cool. Hello, everyone. Really happy to see you back. We actually didn't expect that many people to return, so thank you. And yeah, so we're going to do a little theoretical component, talk a little bit about the algorithms we're going to cover, and after this, we'll implement them and actually put them into the code. And it should be way easier than the pre-processing part where you did the data processing, because it's just like one line of code kind of calling it. All right, so let's just recap with the formulation of the problem. Again, we had the data set, we had the Titanic data set where you have a number of examples where each example is a person, and then what we were trying to do is to predict whether the person has survived or not based on the features that that person had. So either sex, age, name, and maybe their class. And again, our goal was to be just better than the random guessing. So get some loading out of the algorithm, actually have some accuracy higher than 50-50, for example. Right? So the first thing that we usually do is to train the algorithm, we have to split the data into a training and a test set. And the reasoning for it is that you'll be using your training set to sort of iterate your algorithm, and it would learn by itself, sort of see the patterns, compare them to labels, and get some sort of accuracy on that. And then you would use the test set to validate that your accuracy is actually correct. So For example, you might be predicting 100% accurately on your training set, but only 50% accurately on the test set. And the reason for that is that your algorithm only knows how to work with the data in the training set. So you really kind of want to split your data and be able to validate whatever the ideas that, or whatever the understanding you get about your algorithm from the training set and validate it on your test set. And so essentially, your test set is your like real world data, how you would apply your algorithm later on, and essentially unseen data that you might want to use your algorithm in future when you put it in production. Right, and once we have small data sets, we usually do sort of a 20-70, maybe 30-70 split, as you see here. But as soon as we start get into bigger data sets, such as maybe 1 million entries, maybe hundreds of million entries, we sort of start to decrease the amount of the percentage that we dedicate for training and validation sets. So the general procedure would be that you would separate your data set into training, validation, and test set if you have a big enough data set. You would be doing your training on the training set, obviously, and then once you want to tune your algorithm, make it better, maybe find some aspects of the data, you would be using the validation set, and you would never touch the test set until the final production. So the reason for why not touching the test set is really the golden rule of machine learning. It's the idea that the test data should never be influenced during the training of the algorithm. And this is something that we see a lot in really any research projects. You don't want to mess with your data that you have collected because maybe there's an outlier, but this is what you got and this is what you have to set apart and sort of not mess with it to get a better accuracy, not cherry pick the performance statistics. So one of the things that a lot of people do, I am also subject to that, was you train multiple algorithms and you test them one by one and you see whichever one gets a higher accuracy. And just by pure random chance, you might get one that is very accurate, but it's only accurate because of that random chance. So that's why you would only test your algorithms on your validation sets. Maybe you're going to get a very accurate one here, but once you test it on the real data that it hasn't seen before, that's when you're going to see your real accuracy, your actual value. So we mentioned that the test data should not be influenced and it should not be edited. And again, just to recap, we are trying to avoid training multiple algorithms to get a high accuracy, so trying to avoid that random chance of good accuracy. We're trying to reduce cherry picking and performance statistics because we'll cover that in more detail later, but some of the statistics have issues. So well, they might not be representative because of a certain skewed data that you have in your data set. Maybe you have a very skewed class distribution. Maybe only one person died on the Titanic and everyone else survived, right? Then your algorithm can just predict survive and get a 99% accuracy. So that kind of stuff, that's why you want to avoid cherry picking. And you want to avoid changing hyperparameters after testing. So that's, again, coming back to sort of messing around with the test set. And one of the first most basic algorithms that you can start with is a decision stump. And really what it is you choose one feature and you choose the rule that will classify your data set based on one single feature. And you choose the most accurate one. I don't know if this is actually true, but my idea was that if I look at a Titanic data set, maybe the most important feature that is in the Titanic data set is whether the person was a child or not. If they were, we will classify them as a survived, and it wasn't, we'll classify it as a didn't survive. So this is a very simple algorithm, one step, one decision, and you sort of get the answers straight away. But it doesn't mean it's accurate. So what we'll do later, we'll split the training data according to what we just did. So we made a rule that checks whether the person is a child or not, and then we'll split the data into only child passengers or only adults. And the reason why we do this is that we're going to repeat the first step that we did again. We're going to make another decision stump that will be only on the adult passengers data set. So now we're going to repeat that and we'll find another most accurate rule and make sure that it's a different feature. So initially, we thought that the best rule for the whole data set is that the person is a child or not. Now we're only looking at adults. What's the best rule for classifying whether an adult survived or not? Maybe it's whether the passenger was in the first class, because the first classes in the on the ship were on the upper decks, so they had more time to just escape and maybe survive. So we'll make the same rule. We'll say if it was a person in the first class, then they survived. And if they didn't, if they weren't part of the first class, they didn't survive. And now we're going to be stacking those decision stumps that we have created. So now you can see that we're getting a decision tree. So we have a bunch of internal nodes that decide the rules. And in terms of the leaves, we have the classifiers. So has anyone seen decision trees before? Or is it the first time? Nice. OK, so if you're confused, just be happy to ask questions. So essentially, to construct that decision tree, at every point, we'll be subsetting data and choosing the best rule. And this is what we call greedy recursive splitting. We take the most accurate rule, that's what stands for greedy, and then we do it recursively. So every time we chose that rule, we subset the data. So it was the whole data set first, then we chose the greedy rule, is the person a passenger, then we subset data. Was it a child? And only, for example, adult passengers would be the subset. So this allows us to create the decision tree. Our internal nodes are the rules. So there will be this one and this one. And then our leaves are what the classes are that we assign. OK, so once you start building this out, and you might get a very deep tree, something like this, you might get a much better accuracy than just a single decision rule, right? So at each end here, you would get a class, whether it's maybe the orange one is survived and the blue one is died, right? So how do we choose whether the person, how do we choose the best rule? There's actually a lot of different score functions that you can use. One of the main ones is the idea that tries to decrease entropy in the labels and maximize information gain. You don't have to understand too much detail on this rule. You can come talk to us later if you're really interested. But basically, the idea is that at every point when you split the data into two different sub-data sets, you try to make sure that each data set has the most homogeneous items in it. So, for example, if I'm choosing the rule that I'm splitting data set into first class passengers, I want to make sure that the most passengers in this subset will be the ones that survived, and the most amount of in this data set will be the ones that didn't survive, right? So they're very similar in terms of what their label is. And that's essentially what the score functions are trying to do. They're also called loss functions, so you might find that in different classifiers they'll be called differently. Okay, so aside from just choosing a different machine learning algorithm, we can also play around with the hyperparameters of the algorithm. And the hyperparameters are something that control the learning process. And for something like a decision tree, it could be the depth of the decision tree. If we make it very deep, it will be quite good at classifying. If we make it shallow, maybe just one decision, it will be quite bad, obviously. So depth is one of the hyperparameters. Something different could be a splitting criterion. Maybe we split based on a score function that we discussed before, or maybe we use a different one. And ultimately, it could be minimum number of examples in each leaf. So maybe we don't want to split if there's only one person in that class. So for example, we don't want to split by names, for example, because everybody's going to have a different name, and you can continuously split by name, or if he was Peter, then there, if he was Josh, then there, and so on and so forth. But that's not a good learning because you can't generalize that. And what we care about is generalization of our algorithm. So before, we only discussed how to split based on categorical data. So categorical meaning that it's sort of words or sort of questions. But we can also use decision trees for numerical data. And As you can see here, this is the same Titanic data set. This is the age of the passenger, and this is their class. Maybe they were in the first, second, or third class. And what we'll do, we use the same rules to split that subspace. So maybe the best information gain that we can get, so the best rule that we can use is whether the person was in the first class, again. So that would be this line here, the first split that we'll make. Sorry, it's quite hot. So this will be the first split that we make. And then we repeat the split, we say, oh, maybe the age was less than 20. So that would be this square here, for example, right? We can go into that in more detail if you want to ask questions later. Okay, and so we figured out how to construct a decision stump, so a single sort of rule. Then we figured out how to construct a decision tree where you have several rules that stack together to create a classifier. And then the most common classifier that people use in the early stage is the random forest classifier. It's quite generic, it's applicable to many things, and it's quite resistant to any issues in the data. So the way it works, it creates a bunch of trees, and then there's some randomness in it. That's why it's random forest. So it will create, for example, 100, maybe 200 trees, and then let each tree classify the way that the tree thinks is appropriate, and then take the majority vote of all these trees and be sort of more accurate than a single case. So this avoids any issues with overfitting to the data or just learning too much of the details like names, because you have maybe one classifier only learned on names, but the other ones actually learned on relevant features like age and maybe sex, right? So we get much better performance than from a single decision tree. All right, we'll now cover, do you have any questions about the decision trees, maybe decision stumps, just a general idea? It's all good? Okay, then I'll pass you off to Shemaine to introduce the neural nets, which is probably more interesting than decision trees. Question? Did I miss something?
How do you, when we are putting those questions, on what basis we will take out those questions? Like, is the passenger child? How we are coming to those questions?
Okay.
Is there any rule for that, or like?
So the way I did it right now, I was like, oh, hey, I decide the question. But really, that's not what's happening. The algorithm is sort of learning by itself. The way it learns is using the loss functions. So one of those would be this function here, the information gain functions. So it would basically see what kind of rules it can apply, see which one of them does best, and use that as a decision. So kind of choose that as a rule. Right? Is that all good?
Yeah, so I really want to give some basic idea of neural networks, because I mean there are so many machine learning algorithms at the moment, but this is like the algorithm. I mean, this is what actually being used in Facebook, Google, Amazon for most of stuff. And there are many subtypes of neural networks too, but unlike other algorithms, the good thing in neural networks is it is very hierarchical. It's the same thing can be used again and again. You kind of can increase its size, capacity, but it's the same theory. So this is the most effective machine learning algorithm at the moment, and this really means business, I mean, in a way. So if someone asks why we need deep learning, or I think you heard of deep learning, right? Deep learning is another part of machine learning, which you basically use a lot of data and neural networks, right? So the previous algorithm, especially decision trees or maybe support vector machines, you have this feature extraction phase. So even when Jamie was doing this data cleaning part, you guys have seen you have to spend a lot of time on understanding features, getting these distributions correct, and finding out cleaning these features. So this is kind of problematic in in most of real world cases, because you really don't know which features might work first thing, and then the amount of time you spend in on cleaning can be too large. So again, it's not some AI then, it's more like humans are kind of trying to figure out some features. But then what deep learning can do is, like, rather than inputting features to an algorithm, you just can put raw data. You have some set of raw data. It can be a CSV or an image, and the algorithm has the ability to figure out what features I should use. So it is more like computer readable features. So this is, as you can see, this part is really easy, right? You have raw data. You might have some labels. Just put into this algorithm, and algorithm will figure out what features. Maybe those features might be the features that we are thinking, and it's not that exact, but somehow it will give the end result correct. So one problem might be, here you know what features you use. Here sometimes it's not that interpretable, but how people argue against this interpretability is like it's a computer that takes the decision. So sometimes you don't need to go through each and every feature. So like that. So I'll give the basic structure and how this type of algorithms work. So I'm not going into very much mathematics, but if you have a problem, just raise your hand. We can discuss about it. So any neural network architecture is like bunch of weights. So these weights means these weights can be tuned with some kind of an algorithm, and so we call this tuning function, not tuning function, like we call this tuning thing called like, we need to have an objective function, like we need to give an object to the network. This is what you really want to learn. So we call it objective function or the loss function. And then there are like bunch of weights, as I mentioned, they are called trainable parameters. You kind of can tune it, and obviously we need kind of lot of data. So we are talking about gigabytes, maybe terabytes of data. So neural networks are hierarchical. So basically, let's say you need to train a neural network that kind of captions the image. This is one thing. So what you just do it, you just take the image as is and input it to the network. So these are like, we call them neurons. Neurons means like they are like some kind of computational structure, and what happens is these neurons can learn some features. So I mean, saying we don't know actually what it might learn. It will learn whatever the algorithm wants, but we can say here the maybe first few layers kind of can learn very basic features. If it's an image recognition problem, the first layer of neurons might try to find edges of images, those image patches, something like that. And then the middle layer might learn a bit more hierarchical or a bit more global, like bigger features like some hair or ears, nose, and maybe then the final layer kind of trying to combine all together and take the decision. But again, like I'm repeating this again and again, we are not adding any bias, or there's no human involvement when it comes to learn these feature layers, right? So here the task is simple. You have an image. You need to, so your algorithm need to kind of caption it, or let's say algorithm need to say whether it's a human or a monkey, right? So here, so if everything goes right, algorithm will say, oh, this is a human, something like that. And then you'll wonder like, what are these lines? So these lines are weights. So weights means you have an input, you transform that input into some kind of values. So this is like, although this is an image, this is bunch of pixels. So pixels will be transformed into some values by multiplying with these connections. These connections are just random set of numbers. Let's say 0.5 or 0.2, 0.3, something like that. Then you kind of, this is a neuron, you kind of add some nonlinearity. I'll talk about this in the next slide. But the takeaway message is these lines are something that can change, something that is going to change. So in the initial state, these are just random thing. This is very dumb network, but we use some specific technique called backpropagation to train this entire network. So I'll quickly tell about what is this part, actually, these neurons. So let's say these are 3 pixels, right? X1, so 1, 2, 3 pixels. So these are those weights I mentioned. So again, I'm going here. So this is this 3 is just pixels, and these lines are these weights. So these are like some parameters, and this bigger node is this. So what happens is, so you have some input, you multiply those input with some trainable weights, W1, W2, W3. Then you kind of apply some nonlinearity there. So it can be either sigmoid or sigmoid softmax, something like that. So why we apply nonlinearity is, if you know mathematics, if you don't, because if you just keep adding this stuff, let's say there are millions of inputs, and there are like millions of input, and there are millions of weight. What happens is, if you keep adding this will explode. So it's like keep on adding like a sandwich. So having a nonlinear connection kind of squash it down, like it will only try to gather the most important information. But so this is what happened in any neural network. You just get random data and then multiply them with some randomly initialized weight, and kind of apply a nonlinearity. You take the output. So if I go back to that slide again, so then again the same thing happens. You can see. So it happens here. Then the output of this this neuron kind of again get multiplied with some weights, and then this value will be there, and on. So that's why neural networks are hierarchical. So in neural networks, there are like any machine learning algorithm, most importantly, neural networks, there are like 2 phases. First thing is training. The second part is the inference. So as I mentioned, like training is mainly like you need to tune these weights or tune these connections, because they are just randomly initialized. They are dumb in the beginning. So in order to train, as he mentioned, you use a normal data set. Let's say they are labeled with human faces or not, a binary classifier, and you input this data, and then you train it. And once you train it means then you use some specific technique. After that, these connections are now tuned. They actually know how I can extract my features and how I can output my final result. So once you have a trained network, we can just use this to predict. So that's how, like, we just use the copy of this network, and we can use it to predict whether there's a human face or not. So the interesting part is, you might be thinking like how this can get learned without having features or anything, right? So it's a bit of mess. So we call it like backpropagation. You might have heard of it. So backpropagation is basically you have an, let's say, first you input this human face. Somehow the algorithm says this is a monkey, right? So now there's an error. So and since there's an error, you kind of can quantitatively measure that error with numbers. So somehow, if we have a mathematical way to propagate that error, like kind of giving that feedback, oh, you should have identify this as a human face, but you couldn't. So there's an error. So please correct that. So you need to send that feedback again, right? So neural networks comes with this amazing algorithm, which is very easy. It's just like some, it seems a bit complicated here, but it's really, really easy mathematics with some chain rule, we say. So this, you calculate this error, and somehow you propagate this error to each layer or each connection of the network, and network kind of get tuned. So this is one simple example. Let's say this. I think this is NAND gate, something like that. So NAND means one. If you input 1 and 1, it should give 0, right? So these are these random weights I mentioned. So this is like random weights for stuff, and somehow it has output. The output is 0.69, but target should be 0. And now there's an error, right? So the error can be calculated with we call this like mean squared error. I mean, this is the simplest error in machine learning, like mean squared error. This is what your output should be, and this is what the algorithm has predicted. So you kind of get the error and square it out. Then with that error, so this value is how much you need to change. This bigger value is the main value, but these values, like small values, are how much you need to change. So you kind of calculate this error and you propagate it backwards. Then you tune each of these parameter. So end of the day, you will get a nice network without touching anything. You just need to input some input and the output of that thing. So usually we use something called, like, practically we use something called softmax. So you can read about that thing, softmax cross entropy. So the difference of softmax cross entropy is it kind of can highlight. So when the algorithm do a mistake, it highlights, like it's penalized more. That's something like that. It's more effective. It's penalized more, and it kind of also try to understand the difference in between classes, something like that. But so loss function is a key, and you need to understand is you need to have a loss function that calculates the loss between what your algorithm has predicted and what is the real output. Then there's a mechanism called backpropagation, which kind of tune all these parameters. So that's like the basics of neural network. But the lucky thing is, at the moment, you don't need to do anything. I mean, there are like frameworks like TensorFlow. I usually use something called PyTorch. So it's just like 2 lines of code. Will do everything for you. But this is like, it's always good to kind of know the theory. And so again, this is what I explained before. So this is what the backpropagation algorithm is all about. You have an output. This is what predicted. This is the target. So now there's a problem because algorithm couldn't predict the target correctly. Now you kind of calculate this delta. Okay, there's a difference between the expected and the predicted, and then you need to like give that feedback. It's like then we call this like gradient. So So the gradient is more like how much you need to change your value, because in order to get the correct output. So once you do this for larger amount of data, like millions, I don't know, like or billions, so these networks even can perform better than humans. That's the beauty, like especially in natural language processing and other stuff. So so this is purely very much automated learning. All you need is some set of data and some labels, and that's mainly what happens. And how you during a training you kind of can measure how well your algorithm is learning this stuff, because basically you will see there's this delta. This delta might be started in a higher value, but eventually with more steps, with iterative training steps, this value will go down, and this network will learn stuff. So this is the final thing. I mean, just imagine you have two parameters of your neural network. Only has two parameters. So theta 1 and theta 2. So this is the loss. Loss means like the predicted thing. So the difference between predicted and the expected. So what happens is this backpropagation algorithm with other optimizations kind of pushes this loss function towards we call this a local minima mathematically, because usually you can't find the best settings for these parameters, because it's really hard. There's some randomness involved. So with our optimization, what we try to do is kind of reduce this loss. So this is what a neural network training is. Yeah. So this is the last slide. So it's more. This is more like I don't know, mathematical, but it's the same thing. This is 3D. This is 2D. So you kind of your loss, as I mentioned, those weights might be started here or somewhere, because you start this network as a random initialization. Those weights are dumb, and in the start. So after some time, when you try to train, you kind of repeated. This is more like the optimization procedure. Like you repetitively, you kind of sense, oh, there's an error. Try to reduce. There's an error. Try to reduce. So it will eventually go down, and so technically it should go here, but usually in neural network it will stuck in somewhere here, because these are like some problems in optimization, but they kind of works. You don't have to find the best settings. So those parameters can figure out it. So yeah, and this is about like the loss function and the inner workings or the structure of neural networks. So I know this might be a bit overwhelming, but what you need to get is like the general idea, what kind of steps these, because neural networks, I would say it's kind of a different kite, like it has a different set of steps that are not entirely common to other machine learning algorithms. So, but once you learn one neural network, or maybe once you kind of learn how this works, you can kind of use all these new, even like latest algorithm breakthroughs in this domain. And do you have any questions related to this?
Is always there is always a possibility of error when you're putting
Here, the delta.
Yeah.
I mean, so yeah, this is like sometimes randomly you might able to say like it can find, but so let's say when that's why I here what happens is it's more like an iterative process until convergence. Let's say your data set consists of 1 million examples, right? 1 million examples means some 1 million images, and they are labeled cat, dog, rabbit, or whatever, right? So there's no way an algorithm randomly get the correct label for everything, right? So So algorithms kind of need to learn this as a group. Like it's more like an average, right? So in that way, like
That's why that summation thing.
exactly. So it's not just for here. That's a good point. So here it's like this is not this might like it's not just for one example. So end of the day, this is more like average of entire example. Yeah.
And what is that minus log? That value, what is that?
This one.
Yeah.
So we call this softmax cross entropy.
Oh.
So the idea is, so there are different loss functions, right? So minus log likelihood means you kind of can highlight that loss a bit more. Because let's say when you're giving, just imagine when you are trying to give a feedback to an algorithm, if that feedback is strong enough, it's something easy, right? So here what happens is, let's say this is an exponential thing, so you kind of highlight a bit more. So what happens is, let's say you have 3 classes, right? You have 3 classes and cat, dog, and sheep, right? But the correct class is cat. So you know correct class probability. So it's more like what algorithm gave for the correct class probability, and all other probabilities. So yeah, this way what if someone asks in layman terms why softmax cross entropy is good, it kind of can highlight it penalize more when you don't get the correct class, and also it encourages the algorithm to learn differences between 2 classes also. So yeah, exactly. So it's more like you should learn the difference between sheep and the dog a lot, because
You can get better.
yes. So it's more like that.
It's a process.
Uh,
Again, what you're saying.
softmax cross entropy.
It's a process.
Yeah, in a way, it's how you get this. So you get this thing. This thing is pretty straightforward, right?
Yeah.
You have and so yeah. So cross entropy is what process means. It's just like if mathematically it's just an equation, but it's something. It may be a method to calculate the loss. Yeah.
And if anybody is trying to learn this, they need to learn this level of calculus? Or?
Yeah, I would say so. I would say the calculus is the only thing you need to learn. Calculus and probability is the only thing you need to learn deep learning, because when you are trying to learn backpropagation also you need calculus. Like you need to know the chain rule, how you propagate error signal. But it seems a bit complex, but I think this is very basic mathematics if you kind of go down. Yeah.
Yeah, thank you.
Yeah, sure. Anything more? Any question? Okay. All good.
Yeah, okay. So really there's a lot of resources online if you're looking into more detail into into neural networks, and this is not a 20-minute topic. It's really a lot more depth, so feel free to just Google it, find some open source resources, and most likely they'll go in much deeper detail and maybe adapt it for any level. Okay, so one other thing that we wanted to cover is overfitting, and that's one of the main issues that you face in training your algorithms. And so, for example, let's think again of our Titanic data set. Let's say the blue dots are the class that survived, and then the red dots are the class that didn't survive. And then we want to classify and find the boundary, really, between the 2 classes. Our simplest model would be just sort of dividing in the middle, and this would be sort of this just black line dividing it in half. And this is not really representative of what the data distribution is, because there's quite a lot of red dots, for example, outside your boundary. So you sort of underfitting to the data. You're not complex enough to classify your data set. And this is what we saw with decision stumps when we had a single rule that divided our data set in two. So for example, say this is, oh, is the passenger and child? Well, might be yes. So for example, if they are a child, they survived. And if they're not, they didn't. But there's also some misclassification. So what we do, we try to avoid underfitting, but we also are trying to avoid overfitting. And this is more of a learning every single piece of noise in the data set. And as you can see here, this is not generalizable, because if this was our training set and we apply the same sort of boundary condition on our test set, we'll never get the same accuracy because, well, this is just sort of a random outlier, for example. And we want to be able to generalize to new data sets, and we want to be able to sort of use our algorithm outside just the training part. So we need to find that balance between underfitting and overfitting. And what we do to find it, we use evaluation. So one of the basic ideas of evaluation is focusing on what are the possible classifications that you can make and what are possible mistakes that you can make in classification. So the only two correct classifications that you can make is true positive or true negative. So our true positive is what is actually labeled positive and what our classifier labeled as positive. So both the real data and our algorithm agree that this is positive. Same with negative, so that would be true negative. Both the data set label is negative and our classifier predicted it as negative. However, we can also misclassify stuff, and there will be false negative and false positives. So false positive would be something that is actually negative, but we labeled it as positive. Or false negative would be something that is actually positive, but our classifier labeled it as negative. So this gives us a confusion matrix, which is really the matrix of predicted class versus the true class. So this is what our classifier has predicted, and this is what the real label is. And this is how we get positive, positive, we get true positive, negative, negative, we get true negative, and these are the correct ones. And then the mistakes are the negative, positive, right? So any questions about true positive, true negative? A lot of true stuff in there? Okay. So the reason why we're creating this confusion matrix is this is how we deduce the accuracy of the algorithm. What we are particularly focusing in here is the precision and specificity, or another way to call it is recall. These are the two metrics that are most often used. And what precision is really your true positive rate. So what are the classes that you classified positive out of all the classes that you classified positive? So I might be classifying, I don't know, 100 classes positive, so 100 examples positive, but only 10 of them are actually positive. So my precision rate is 0.1. And then the specificity would be the how much I classify as negative and how much of that is actually negative. So the sum of true negative and false positive. So true negative divided by the sum of true negative and false positive. So how much of the negative things that I classified negative are actually correct. So using that, we can derive an accuracy metric, which is derived according to this formula. And this is most generic metric that you can use for your classifiers or for your just general machine learning. And the only reason that is important is that it suffers from the being misleading on an imbalanced data. So remember how I mentioned about the very imbalanced data set where we only have one person who survived and everyone else died? In that case, our algorithm can just our accuracy would be 99 even though we don't predict well at all. Because, well, in the distribution, 99% of people die, so I might as well make prediction that this person died just by default, even though I don't know anything about the features. So there's certain ways to avoid it. We can look in that into more detail later. And another metric could be the F1 score, which slightly avoids that imbalanced issue, which takes the sort of the mean value of precision and recall, or precision and specificity. All right. So ultimately, the final steps, after you've done your training, after you tested your training, you tested your model on the validation set, you're happy with your hyperparameters, you're happy with whatever accuracy you got on your validation set or on your training set, you would retrain the model on the whole data set and put it into production. That's really the final step that you would always do. All right, any questions on the evaluation part? Cool. Shall we jump into the implementation of whatever we just covered? Perfect.
So basically, to do, so we're using the scikit-learn library. Okay, I can, that's fine. I'll just go through the actual thing. I don't know why it's green. I'll just do it on the lectern.
So I wanted the code.
So there's a few, earlier in the day you learned a few algorithms, right? They were all somewhere here, I believe. Supervised learning. You learned the decision trees and also the random forest, which is, where is random forest? Okay, so you've got the random forest here. So what we want you to do in your, so Michael went through how you can create a decision tree classifier, and then we want you to create a random forest classifier. So we'll just go to, great. Because I realized we don't have that database either. Can we do it without signing in? I'll just do it here anyway. Would have is okay, I will sign in. Oh, there might be too much shit there actually. This one was not working, right? Oh, okay. The code's up there if you want. But basically, your goal is to. Oh, great. It was there.
it was there. Do you want to
Just go to my.
Yeah, it is. It was on there.
On
But
mine?
but it's not showing. Is the
Why? I don't say something wrong first.
Seems like Mac is just rejecting.
That's not a Mac item. Great one.
okay? It was there.
Do you want to? Yeah.
It's green again.
Use this one, yeah, use this one. I don't think I had a problem with this one.
Just using the document. You broke it even more. Why is it even more broken?
You should show him that as well.
Is it because this is off, that one's off?
Doesn't detect it. You should put broken away.
Well, where was the double as well? Then it's gonna go green again, isn't it? Why is this so much harder? Explode. No, this is gonna go green again. Don't skip. Wait, why is it? Well, that's how it was before. Can you see someone else skip it?
Seem to keep clicking on that.
It's not even going on there.
You have to click on this.
Please work.
Dies after like 2 seconds.
Why? Don't say that.
It died again.
God.
Can you use someone else's computer?
Just finish off the course after that. You got on. Wait, how are you going to show course after that?
It's just a picture, right?
Cool.
And I will. Do you want the? Because I think you can do the. I'll just upload this whole thing. No, I can't. Where's Pete? Okay. You can't open up other numbers here. Have you guys trained a random forest and a perceptron yet? Or hands up if you've trained a perceptron on a random forest? So basically, your task was basically to change one line of code from the decision tree classifier. So changing the model is basically one line of code. Peter, do you want to explain cross-validation? So next we'll be doing some cross-validation.
Awesome. So one of the things that we discussed before was actually the idea that you can get a good answer randomly. And if I train 10 random trees, I'll get one that's much better than the other ones. And essentially, there will be the accuracy of those trees will be normally distributed around some real accuracy. And this is where we use sort of cross-validation technique, which is partitioning the data set and then getting a multiple accuracy results and then being able to justify that your algorithm is statistically significantly actually this accurate, not just some random number that you got once in a lifetime. So essentially the idea is you would take, for example, this is a 5-fold cross-validation. You would partition your training data. So you would take your training data and you would partition it into sort of 5 sets, each worth 20% of the data set. And one of them is going to be a validation set, which is in blue. And one of them is going to be, 4 of them are going to be the training set. So the first split that you do, you'll be training using these 4 subsections of your training data. And you'll be testing it on the fold 1. Then when you do the second split, you would be, you got 1 accuracy from here. Then you're going to be running it on the second split. You'll be using the first, the third, the fourth, and the fifth sort of subsections of the data, training on that section, and then testing on the fold 2. And then you repeat that 5 times. You'll get 5 different accuracies. And this is sort of your average accuracy of the algorithm. And really, it doesn't have to be 5-fold. It can be 10-fold, which is most commonly used. It could be n minus 1-fold. So if you have a data set of 100, it could be 99 to 1 kind of thing. And it gives you a good understanding of how well your algorithm performs because you're really utilizing all of your data. And you don't do that sort of, I'm only going to look at these 80% of the data. No, you're looking at 80 in different subsections. So you're actually looking over all data in the end. Right? Is that all good? Any questions? Cool.
Question.
Oh, sorry.
Yeah, how do you decide like each of the folds? Is it a completely random process? And then otherwise, like in between different splits, would fold 1 like be in like split 1, for example, be the same as fold 1 and split 2, and it's just one fold you choose each time? Like, is it different?
Yep. So the way it works, you would first shuffle the data before you do it. So there's an actual function called shuffle. You shuffle the data, you get completely random distribution of your samples, and then you would split it into 5 sets, and then you would keep those 5 sets for the whole training step. You would not reshuffle it. So your fold and fold 1 will be the same as the fold and fold 2, and the same as fold 1 and fold 3, and so on. So every split, each of those fold 1, fold 2, fold 3 are the same subsets. You don't reshuffle them. Cool. Is that good?
I got a question. So for the cross-validation, do we need to split the training data for the test data and the training data?
So you're normally doing it on the training data. So one of the advantages of cross-validation is you don't have to use the test data, so you can get an idea of the accuracy of the model without looking at the test data. Yeah.
And if you're doing your PhD, you still need a test data. Yeah. No, like for really formal academic work. Yeah, but for what we do, it's okay. Yeah. Awesome. I think we can come back to the implementation.
Michael, do you want to do the cross-validation code with just this? is that enough?
Yeah, I think you don't even need to go over it. So we'll just finish up with cross-validation. So you just saw the concept of cross-validation. Applying cross-validation inside of sklearn is much more easier than actually doing the fit and then predicting stuff. So we want to just assess like that we're not actually getting a really good model out of randomness, so we just cross-validate it here. So we have cross-val score, which is the method inside of sklearn, and then we can chuck in our classifier here, so it's decision tree classifier here, and then we just chuck the X train, the Y train, and then number of folds we want. So generally you would use 10 folds. So we just chuck 10 here, and then we'd get all the scores. So the scores here is an array of 10 numbers, which outputs the accuracy of each individual model that you train on the fold. And then we can just get the mean of that array and then the standard deviation of it. And so that means we get an 80% accuracy with a 4% standard deviation. And yeah, so you guys can do that. The difference between this and just fitting, you just have to chuck the model in here. So the first parameter fed into it is the classifier that, or model you're trying to use. So here we have perceptron, and then we have random forest. Otherwise, it's all the same. Cool?
Yep. The number of folds basically splits the number of rows in the data set. So it's basically like if you've got a 1,000 row data set, it'll split it into 10 100 row data sets.
So yeah, so when you're doing the splits, you're basically doing it by rows. So if I, for example, had 100 observations in the training data, and we want to do 5 folds, row 1 to 20 would be the first fold, and then so on and so on. So when you do a shuffle, you're basically taking at random the rows. What's this one? Cool. So I think 5 minutes on cross-validation, and we will move on to neural networks.
Try to run it actually.
Just get it from that thing. Oh, I think they need to go. Let's go. Okay.
I can just change the.
Can you just not point at the whole thing? Just point at that whole like folder.
I think it does. I think it only does the one because you can't do the
Okay.
test.
Let me scroll down so we can see.
Oh, test.ca. Okay. No test labels. Okay.
Where's the?
It's train clean, test clean, and test.
Oh, because Jamie removed the things. I need the labels.
I can probably start from the. Yeah. Oops. Passenger ID.
Just but don't worry about it. I'm just coming.
Oh, I think it might be because it's sometimes it's in the middle of uploading. doesn't actually upload the whole thing.
Yeah. Missing. No, don't worry about that.
Yeah.
Don't worry about that block. Just comment it out. Just comment out the whole block, because this is it.
Yeah, I'll just do this then. Yeah. Maybe. Should I do another?
So you just need to apply the scalar on the data,
Yeah.
and then put it in.
I'm just thinking I'll do as a refresher. I'll start from scratch.
Okay.
Am I still on the same? No, I'm not. Okay, I'll start from scratch from here. I'll check the other ones. Have you guys trained the what is it? What were we doing? Cross validation. So as a refresher, I will just go through the whole process again. If you were to start from scratch with a notebook. So I'm assuming you have a folder with that you're running the notebook on, and with a data folder with a clean data set. So the first thing you have to do is to import the libraries, right? So we were using pandas and NumPy. I think this part might be too easy, right? And assume we have the and then the input is, I think we just did this. So. We'll go through so what we're using for the machine learning is the scikit-learn library, right? So there's a lot of models that you can choose from. So we'll be looking at neural networks. And the most simple one is the multi-layer perceptron. So if you Google scikit-learn, you'll be able to get to this documentation, and then you can see what you need to do to train the model. So you'll just import what you need. So we'll be using the multi-layer perceptron classifier. Multi-layer perceptron is basically another name for a basic neural network. So the MLP. So we first need to basically, this MLP classifier thing that we just imported has a bunch of parameters. So the first parameter is the number of hidden layers of the neural network. And there's a bunch more parameters like the activation function and things. But basically, the hidden layer sizes, the hidden layer parameter, if you go here, it is a tuple that basically you need to specify the number of neurons in each layer. So if you have a 3-layer, if you want to build a 3-layer neural network with each layer having 150 neurons, you'll put 150, 150, 150. And that'll basically create a neural net with 3 hidden layers, each with 150 neurons each. And there's other parameters you can, what do you call it, methods. You can add other arguments you can add, such as the activation function. You can change the optimizer, and there's a whole bunch of learning rate and things. So after you can play around with these, but scikit-learn usually has pretty good default parameters. So after you've got your classifier, you need to, right here, so you need to train it. So to train the model, you go, after you've got MLP classifier. After you define your network, you have to train it. So you fit it, and what the fit function wants is the input and the output, so the X and the Y. So the X is going to be the X train that we created before, which looks like this, which basically has all the columns except for the people who died, the survival column, and then the Y is basically if they survived or not. Y train does not exist. What did we name it? Capital Y. So 0 means they didn't survive, and 1 means survive, right? And then we fit that. And then after you fit your model, what do you have to do? Predict. So you can predict on the stuff that you have not. You can predict on the Y. So you can try to make predictions on the data that you don't have, that you don't know the answers to, which will be the Y test. So you can just do one. Let's try. So let's look at this passenger here. So it's got a class of, they were on 3rd class, and so these are basically the features. So they were on the ground floor, and it is a guy, so I was right about the gender, I guess. So if you want to put this person into the model, so we just put it into the model. So we named it MLP classifier, so we have to say MLP classifier.predict, and then we can put this in. Hopefully that works, otherwise the format it's wanting is in the same format, so I'll do this. So it's basically the same thing as what I showed you, but the format is slightly different. So we put that into the model, and it'll give you a prediction and that prediction is a 0. So that means the model thinks that this person will not survive, I believe. And then you can do this not just for this one person, you can do this for the first 10 or the first 100 people. Let's do it for the first 10 people, and then the model thinks the 1, 2, 3, 4, 5, 6, 7th person and the 9th person will survive. And then, but that we can also see here in what it will use as the score. So if you go right down, it'll tell you what the score parameter gives. It's also asking for an X and Y, and it returns the mean accuracy of the given test data and labels. So if we put, where were we? So into the MLP classifier .score, we put the entire, it's expecting the X and the Y. So the X test and the Y, is it the Y pred? We will check. It'll give you the score, which is that it is 80% accurate on the test set. So we can do the cross-validation for this as well, but we'll do the cross-validation as well. Where's the cross-validation? So the cross-validation, we want to put the model, which is this one here. We put that in here with the training data set. So it's the X and the Y. So if you do, usually Shift Tab works in most things, but sometimes doesn't. So scores is basically, it might take a while because it's not the smallest neural net. We'll let that run for a little bit. So scores is basically an array. So in the 10 cross validations we did, the first split gave a score of 67%, 67, 75, and the sum of these were 82%. So you can just do mean to check the average accuracy, right? So that's on average 73% accurate, this model. And then, yeah, that's about it, I think. Anybody else anybody has questions? No questions? Okay, I think that's basically the model training part done. The final part for today is basically the Power BI stuff. So, which is basically visualizing the data so you can present the data, and you can also basically calculate the outputs from the model and present it to somebody else. And Power BI is quite useful in sort of the presentation of the data. So I'll give it to Chalu to do the Power BI.
Okay. Where's the microphone? Ooh. Hello. Hi. Okay, so we're just gonna go through Power BI, and it's basically just this tool for visualizing data in a way that makes it more interpretable to like an average viewer. And it's not necessarily directly related to all the Python that we've been doing today. It's more on the practical visualization, like nice charts and stuff like that. So it's useful in like a business setting, not as mathematical as everything else. So it's gonna be quite different from what we've been doing. But I'm not gonna make you guys go along with me just because then we're gonna have to install it all over again and everybody's gonna have to go at their own time and stuff. So I'm gonna walk you through what you can do with this tool. So yeah, it's a pretty like popular tool to use for like business analytics and stuff like that. So yeah, so basically what you need to do first is get your data. And the way that we've been cleaning our data today wouldn't be directly relevant to the way that we're using Power BI. So I'm going to be using the Titanic data set cleaned differently. So when I import it, you'll be able to see that it's pretty different. Ooh. Whoops. Okay. Sorry. So this is the way that our data looks for Power BI. So it's not all ones and zeros and everything. It's just how it would look like if you import it into Excel. So hold on, I'll just try to find it. So yeah, here you can see like all the different columns that are in the data set and all of the applied steps to change the data within that. So in the original data set, there was no age range column. And the way that I added that was you go to age and add column from examples. And this basically bases the new column on the data from the old column. So if I based it on age, I based it on age and I put 20 to 24. It would, since I already have this column, I don't think it's reading everything, but basically when you put 20 to 24, it reads the entire data set and autofills everything for you. So the entire age range column was auto-generated by Power BI. So if you go back to home, these are basically the different charts that you can make with this tool. So here you can see total passengers, and the way that you do this would be to click on new measure. And this is kind of like the thing that Power BI is known for, sort of creating new measures to like define your data and stuff. And you could do, for example, passengers count is equal to count, and you count the number of tickets that were sold. So Titanic data, ticket. And if you put in card and drag in passenger count, it would show that there were 1,309 passengers on Titanic. So yeah, that's pretty much what that is. And then for survivors, you could do the same with new measures, and you'd be able to calculate survival count equal calculate passengers if the survived column was equal to survived. And yeah, so if you had the card, you'd be able to do that. And it would show that there are 500 survivors. So yeah, these are the sort of visualizations that you could do. And then this is just a basic pie chart, so I can just do that again. And if you just click on this, which is the pie chart, drag in any data that you want to visualize. Say that you'd want to see how many of the passengers were male versus female. You could put that in here. And passengers. And it would show the proportion of male to female. And it alters the data around your workspace. So it's a good way of like showing how variables change based on different attributes and stuff. So yeah. So those are just really basic visualizations that you can do. There's also bar charts here. So if you want to do a bar chart, and based on age range and passengers, then you could see how many were in those age ranges. Yeah, and then you could also see like what influenced people to survive in the Titanic. So it would be this, which is basically this key influencers visualization feature. So if you drag that in and you analyzed survived, so whether somebody died or survived, and you explained it by class, age, range, gender, Power BI will sort of work these things out for you so you can see what the key influences are. So you're most likely to survive the Titanic if you were a female in first class, if you embarked on like in this port, and if you were between the ages of 0 and 20. So yeah, there's like Power BI solved all of this for you. You didn't need to code any of it and stuff. And you can see like the top segments and sort of break that down. And yeah, it's just a cool way of putting everything together and being able to present this in a way that's understandable to everyone. So yeah, and then you can learn more, and it just tells you all these things about the data. And yeah. So yeah, and then you can create a decomposition tree, which is also pretty useful. So for example, you start with 500 survivors. You'd use this tool over here, which is the decomposition tree. You start with 500 survivors, and then you could explain it by the different variables, like we did with the key influencers one. And then every time you click plus, you could see which one had the highest value, the lowest value, or you could customize it yourself. So we'll go with high value and see. So out of all of the 500 survivors, 339 were female, 161 were male. And then you could see out of that, high value again. Most of them were between 20 and 40, and then high value again, and most of them were first class. So yeah, it sort of just decomposes from like the bigger group into little smaller segments and makes the data more interpretable. And you can see sort of the relationships between the variables and stuff like that. So yeah. And then there's a new feature that you can use. It's within, they're still like testing it out, I think. I don't think it's officially been released, but if you went to options and settings and preview features, and you used and you clicked on the smart narrative visual tool, you'd be able to do sort of auto-generated summaries of your data. So without this, for example, if I just deleted this, whoops. Okay, just pretend that this isn't there. If you clicked on this and clicked on summarize, you'd be able to generate like a smart narrative about the data. So basically it would tell you things about the bar chart that are present from the data set. And you wouldn't need to write these out yourself. So yeah, Power BI stands for Power Business Intelligence, and it's pretty much that. It does a lot of the work for you and stuff. So yeah. Anyone have any questions?
So and for age, some of the ages are blank. So just to check, would that be where on the table there wasn't any data for age?
Yeah, if you originally didn't filter it, I actually already filtered it, but if I selected all, you'd be able to see that there would be a whole column with just blank, it would just be blank, but you wouldn't necessarily want to present that because that doesn't indicate that much, so you would just filter it, select all, and then untick blank, and so you wouldn't have that, and it wouldn't change anything within the data, it would just remove that entire sort of group. So yeah. We're done.